Hi everyone, and thank you for joining. Today I will be presenting my work titled Deep Reinforcement Learning for Beam Angle Optimization in Radiotherapy Planning. This work focuses on automating the highly manual task of selecting optimal beam angles in IMRT, intensity modulated radiation therapy, using a deep Q learning agent that learns anatomical dose trade-offs directly from data. I will walk you through the clinical motivation, the machine learning pipeline, the training methodology, performance results, and the limitations and future direction for deploying this approach in real clinical environments. Radiation therapy plays a vital role in treating many cancers by delivering precise, high energy radiation doses to tumor volumes while minimizing exposure to surrounding healthy tissues. However, achieving this balance is far from straightforward, and one of the most critical yet difficult components of treatment planning is beam angle selection. Every choice of beam angle influences how the dose distributes through the patient's anatomy. The planner has to consider multiple competing factors, ensuring full tumor coverage, avoiding organs at risk like the spinal cord or parotid glands, and maintaining dose uniformity across the treatment area. The challenge lies in the fact that these trade-offs are inherently multi-objective. Tumor coverage often competes directly with organ sparing. Because of this, clinical planning has traditionally relied on human expertise, iterative trial and error, and visual intuition developed over years of experience. This dependence on manual adjustment makes the process slow, subjective, and highly variable between planners and centers. As cases become more complex and adaptive, radiotherapy workflows require rapid plan updates. Manual beam selection becomes a clear bottleneck. So now let's talk about specifically the beam angle optimization in IMRT, also known as intensity modulated radiation therapy. In IMRT, radiation beams are shaped and modulated precisely, but their entry angles still fundamentally determine how radiation travels through healthy tissue and reaches the tumor. So even with advanced beam shaping, the choice of angles plays a major role in treatment quality. However, selecting angles is extremely challenging. Even with a limited set of possible directions, the number of beam combinations grows exponentially, making exhaustive search and computationally infeasible in a clinical setting. Instead, physicists rely heavily on experience and trial and error, which can take hours to refine and introduces variability across clinicians and centers. There are strong clinical trade-offs. We want to maximize dose to the tumor for effective control while minimizing exposure to nearby organs at risk. That balance forms a complex, non-linear optimization problem that is difficult to solve manually and time-consuming to iterate on. So beam angle optimization is a perfect candidate for automation, sorry. Not only to reduce planning time and workload, but also to standardize quality and support adaptive same-day radiotherapy workflows. This slide highlights why automation in radiotherapy planning is important. Manual beam angle selection can take hours and relies heavily on planner experience. With deep reinforcement learning, we can cut that planning time dramatically, potentially down to minutes, enabling faster workflows and making adaptive radiotherapy much more feasible. You can also see that automation improves consistency. Different physicists can produce different plans for the same patient. By using a trained model, we enforce consistently high quality planning across centers and across planners. Another major benefit of this is personalization. Instead of relying on standard beam templates or manual trial and error, the model learns those anatomy relationships from data and tailors beam selection to each patient's unique anatomy. Eventually, automation also helps in scaling expertise. Not every clinic has highly specialized staff or time for complex planning. An automated RL agent democratizes high quality planning, supporting institutions with fewer resources and reducing overall planner workload. So overall, automation here means faster planning, more consistent plans, better personalization, and broader access to expert level treatment quality. Now let's walk through how beam angle planning in radiotherapy has evolved over time, because it helps motivate why reinforcement learning is the right step forward. We started with manual planning, where experienced medical physicists would manually adjust beam angles based on clinical intuition and anatomical understanding. This approach works, but it is a highly subjective and depends heavily on individual expertise and often requires a lot of trial and error, which can prove to be quite cumbersome. Then we moved into optimization based algorithms. Approaches like simulated annealing, genetic algorithms, and gradient based methods allowed us to systematically explore the search space. These methods introduce rigor, but the problem is that the beam angle search space explodes combinatorially. So fully optimizing angles for every patient becomes a very computationally expensive and impractical in routine clinical settings. Next comes heuristic strategies, such as beam eye view metrics and geometric rules. These methods speed things up by applying handcrafted heuristics, but they still rely on predefined assumptions and cannot fully capture the complex clinical trade-offs between tumor coverage and organ at risk sparing, the OAR sparing. Now we arrive at reinforcement learning. Reinforcement learning presents a fundamentally different paradigm. Instead of hand-coding heuristics or trying to exhaustively search the space, we train an agent to learn optimal beam angle decisions directly from patient anatomy and dosimetric feedback. It is able to capture nonlinear trade-offs, handle delayed reward signals, and potentially generalize to new patients without manual tuning. In other words, RL gives us a data-driven decision strategy that learns the same intuition as an expert planner, but in a scalable and reproducible way. So this slide really tries to illustrate the natural progression from intuition to systematic search to heuristics and now to learning based optimization, which combines accuracy, efficiency, and scalability. To train our beam angle optimization model, we use the OpenKBP dataset, which serves as an open benchmark for radiotherapy dose prediction and optimization tasks. It is one of the most comprehensive public datasets in this domain and can be also found on Kaggle and provides all the necessary clinical components for developing and evaluating learning-based planning systems. The dataset includes several key elements. First, we have the planning target volume, or as we are going to refer to it throughout this presentation, it's PTV, which represents the tumor region that must receive the prescribed radiation dose. Then we include 5 critical organs at risk, OARs, the brainstem, spinal cord, mandible, and the left and right parotid glands, all of which must be protected from excess radiation exposure. The dataset also contains ground truth dose distributions, essentially the clinical dose maps created by expert planners which serve as our supervision targets. And finally, it includes the CT imaging data, which provides high-resolution anatomical reference for spatial context. In terms of pre-processing, all patient volumes were normalized to a 128 by 128 pixel resolution for computational efficiency. We constructed an 8-channel input representation by combining the CT intensity map with binary masks for the PTV and each of the 5 OARs, along with a combined structure mask. This representation effectively encodes both anatomical geometry and the evolving dose information, making it suitable for convolutional architectures. To handle volumetric data efficiently, we used a slice-based training approach, where each 2D slice is treated as a sample. This not only improves training throughout, but also preserves the spatial anatomical relationships needed for beam angle reasoning. So overall, the OpenKVP dataset provides a clinically realistic foundation. ensuring our reinforcement learning model learns from authentic, high-quality treatment data. So on this slide, I'm showing two example patients, patient 7 on the left and patient 46 on the right. These are completely random. What you're looking at here are axial CT slices overlaid with the planning target volume or PTV highlighted in cyan. The PTV represents the tumor region that we need to deliver radiation to with high accuracy. These examples illustrate two important things. First, you can see the anatomical complexity in head and neck radiotherapy patients. The tumor shapes are irregular, the surrounding anatomy is crowded, and critical organs are located extremely close to the target. This is exactly why optimal beam angle selection matters. Even a small deviation can either underdose the tumor or overexpose sensitive tissue. Second, notice the variation between patients. Patient 7 has a more centralized and compact PTV, whereas patient 46 has a more elongated structure located laterally. This variation highlights why a learning-based system is useful. Manual rules don't generalize well across anatomy, and traditional heuristic planning might struggle when geometry shifts significantly. In our pipeline, these anatomical masks are part of the input to the reinforcement learning agent. The agent observes the CT structure, the tumor mask, and organ at risk masks, and learns how to consistently select beam angles that maximize tumor coverage while limiting radiation to nearby structures. So, these images demonstrate both the challenge and the motivation. Patient anatomy varies widely, tumor geometry is complex, and automating the decision making can help ensure consistent, high quality planning across diverse cases. Now that we have seen the clinical motivation and the challenges in radiotherapy planning, let's talk about what this project is fundamentally trying to achieve. The core objective of this work is to enable autonomous beam angle optimization using deep reinforcement learning. In simpler terms, we want the system to be able to look at a patient's anatomy, understand the trade-offs between tumor coverage and organ protection, and automatically propose optimal beam directions without manual trial and error by clinicians. There are three major components to this goal. First, we aim to learn optimal beam angle policies. Instead of manually exploring thousands of possible angle combinations, the DQN agent continuously improves by interacting with dose simulations and learning which angular sequences lead to the best radiation delivery patterns. So the system learns purely from the dosimetric consequences of its actions. Similar to how reinforcement learning agents learn to play complex games like Go or StarCraft, but here the game is balancing cancer treatment accuracy and tissue sparing. Next, we want to ensure the learned policies generalize across patients. Medical AI must work reliably on new anatomies and tumor presentations. So our pipeline is designed to validate performance on held out test patients and unseen geometries, demonstrating that the model isn't just memorizing patterns but actually understanding underlying radiotherapy principles. Finally, the long-term vision is clinical translation. That means providing a framework that can be integrated into treatment planning systems. If successful, this approach can reduce planner workload, eliminate manual variability, and support adaptive radiotherapy, where plans are optimized daily or even intrafraction, something that is nearly impossible with fully manual workflows. Overall, the goal is to move toward intelligent, data-driven radiotherapy planning systems that support clinicians and elevate treatment quality, consistency, and efficiency. This slide summarizes the expected impact of our work across three dimensions: technical, clinical, and research. Starting with the anticipated outcomes, the automated beam angle selection system is designed to deliver treatment plans that match or even exceed the quality of expert dosimetrists. By automating this step, we can reduce planning time drastically, potentially enabling same-day adaptive radiotherapy sessions. The model's outputs are consistent and reproducible, eliminating planner-to-planner variability. And we also benchmark performance quantitatively against both geometric and heuristic beam angle optimization methods. Overall, this helps achieve better tumor coverage and improved OAR sparing through learned anatomical and dose relationships. From a broader clinical perspective, this work frees up physicists' bandwidth, especially for complex cases, and standardizes plan quality across institutions. That's critical for scalability, especially in resource-constrained environments where expert planners may not be available. Finally, from a research standpoint, this project stands to be one of the few fully automated deep Q network beam angle optimization frameworks trained and evaluated on an open clinical dataset. It also introduces a reinforcement learning formulation tailored specifically for dose-driven optimization, offering a foundation for future adaptive and personalized radiotherapy models. Now let me walk you through the system architecture that powers our reinforcement learning based beam angle optimization pipeline. The entire workflow starts with the patient's CT scan and segmentation masks. We input a high resolution CT slice along with binary masks for the planning target volume and all organs at risk. This gives the model anatomical context. It knows where the tumor is and where the critical organs are located. Next, the DQN agent comes into play. Instead of choosing all beam angles at once, the agent selects one beam angle at a time. After each choice, it observes how the newly added beam changes the dose distribution. This incremental decision process allows the agent to strategically build the final beam configuration step by step, just like a human planner would do, but much faster. After each beam is selected, we perform a fast dose update. This simulates how much radiation that beam contributes to each region inside the body. The dose map updates cumulatively, meaning that the agent sees the evolving dose landscape after every step. So over time, it learns how different angles interact and how to balance tumor coverage with organ sparing. Finally, after selecting 5 beams, we evaluate the plan using clinical metrics such as PTV coverage, D95%, and OAR mean dose. This serves as feedback for the learning process, guiding the agent towards clinically favorable decisions. In essence, this system enables adaptive beam planning. The agent continuously responds to the dose distribution it creates, refining its choices in real time. It simulates how expert radiation oncologist thinks, but does so algorithmically and at scale. This slide describes the core deep reinforcement learning model that drives our beam angle optimization, the Deep Q network or DQN. The DQN is designed to process a 9-channel spatial input that captures both anatomical and dosimetric information about the patient. Essentially, it takes a 2D slice of the patient anatomy along with the cumulative dose delivered so far and learns to predict the best beam angle to use next. In the input layer, we provide 8 anatomical channels, which include the CT slice, the planning target volume mask, and the 6 OAR masks for the brainstem, spinal cord, mandible, and the left and right parotid glands. The 8th channel is a combined OAR representation that captures their aggregate spatial distribution. To this, we add one more channel representing the cumulative dose map, making a total of 9 input channels. Each of these channels has a resolution of 128 by 128 pixels. Now moving to the architecture, the model uses convolutional layers to extract spatial features, essentially learning how dose gradients and organ boundaries relate to each other. These spatial encodings are then passed to a fully connected layers, which map them to Q values. Each Q value corresponds to one possible beam direction, from 0 degrees to 350 degrees in 10-degree increments, giving us 36 possible actions. The key innovation here is that the network doesn't need explicit geometric rules or handcrafted dose models. Instead, it learns these spatial relationships directly through end-to-end training, optimizing beam selection based purely on dosimetric rewards. This allows the DQN to inherently balance tumor coverage and organ sparing, learning a policy that mimics clinical intuition but is entirely data driven. Now we have a code snippet, and this code defines the CNN architecture used by the DQN agent. At a high level, it takes in multi-channel medical images, including CT slices, target volumes, and organ masks, and processes them through a stack of convolutional layers to extract spatial and anatomical features. After these convolution layers, the output is flattened and passed through a few fully connected layers for each beam angle. The final output represents Q values for all 36 possible beam directions, essentially telling the agent which angles are most optimal given the current dose distribution. In simpler terms, this CNN acts as the agent's vision system, allowing it to interpret patient anatomy and dose patterns before making its next decision. Moving on, we are now going to look at how the reinforcement learning environment represents the state for the beam angle optimization tasks. Essentially, this state captures all the information the model needs to make a decision, both about the patient's anatomy and the current dose distribution. The input to the network is composed of four major components. First, we have the CT slice, which provides an anatomical density map. This serves as the spatial reference for all dose calculations. Next is the PTV mask, which delineates the planning's target volume. That's the region where we want to deliver the therapeutic radiation dose. Then we include OAR masks, which are binary maps for the organs at risk, like the brainstem, spinal cord, mandible, and both parotid glands. These are critical structures that we need to protect during treatment. Finally, there's the dose map, which records the cumulative radiation dose so far. After each beam selection, this map is updated to reflect the evolving dose distribution across the anatomy. Together, these channels form a 9-channel input representation, allowing the model to learn how dose, tumor geometry, and organ proximity interact. This setup enables the network to reason about complex trade-offs between tumor coverage and organ sparing dynamically as it plans each subsequent beam. This slide explains how the reinforcement learning agent makes decisions about beam angles. In our setup, the agent operates within a discrete action space consisting of 36 coplanar beam angles, each separated by 10 degrees, covering the full 360 degree around the patient. During training, the agent doesn't select all beams at once. As we discussed earlier, it uses sequential selection, meaning it picks one beam at a time, evaluates its effect on the dose distribution, and then selects the next one. To avoid redundancy, action masking is applied so that previously chosen angles are removed from future options. We also use an epsilon greedy exploration strategy. This allows the agent to balance exploration, like trying new beam configurations, with exploitation, which is selecting known effective angles based on learned experience. Overall, this formulation keeps the search space manageable while still clinically realistic. For example, in head and neck radiotherapy, typical treatment plans use around 5 to 7 beams, and this model design reflects that practical balance between accuracy and efficiency. Now let's walk through how the reinforcement learning agent actually chooses beam angles during planning. This snippet implements the core action selection logic. The key idea is that the agent must pick one beam angle at a time out of 36 possible angles without repeating any previously selected angles. We first define a discrete action space, beam angles from 0 to 350 degrees in 10 degree steps. The agent will ultimately choose 5 beams sequentially. Inside the select action function, the state is converted into a tensor and passed into the Q network. which outputs a Q value for every possible beam angle. We then apply epsilon greedy exploration. With probability epsilon, the agent explores by picking a random angle from the available ones, meaning angles that have not already been chosen. This encourages the model to try new configuration instead of always picking the current best guess. When not exploring so during exploitation, we use the Q network predictions. We mask out the Q values of angles that have already been selected by assigning them a very large negative value. This ensures the agent never reselects the same angle. Finally, we simply return the index with the highest Q value among the valid options. That becomes the next beam angle for the treatment plan. So this logic ensures three things. The agent respects clinical constraints, no repeated beam angles. It balances exploration and exploitation during training, and it selects the beam sequentially, mimicking real treatment planning decisions. Now that we understand how the agent perceives the environment and selects actions, now let's look at how it learns to make clinically meaningful decisions. The reward function is the core of this process. It converts radiation oncology objectives such as tumor control and OAR sparing into numerical signals that the reinforcement learning agent can optimize. In radiotherapy, the primary goal is always to achieve high tumor coverage while keeping doses to healthy organs as low as possible. To encode this, we design a multi-term reward function. The first term encourages strong target coverage by rewarding the percentage of the planning target volume receiving at least 95% of the prescription dose. This pushes the agent to ensure that the tumor consistently receives therapeutic radiation. The second term promotes dose homogeneity inside the tumor, measured using the D95 metric. That is, the dose delivered to 95% of the target volume. Improving this drives more uniform and clinically reliable dose delivery rather than leaving regions undertreated. Next, we penalize mean dose to OAR. This component models a toxicity risk and pushes the policy to learn anatomically intelligent beam configurations that naturally avoid critical structures like the spinal cord, parotids, and mandible. Finally, we apply a small penalty for using too many beams. Clinically, while more beams can help sculpt dose, they also increase treatment time and complexity. So this soft constraint encourages efficiency without compromising dosimetric quality. Weights for each term were selected based on clinical reasoning, specifically oncologist input and contact guided dose tolerances, giving target coverage the highest priority, followed by dose homogeneity, organ sparing, and lastly beam count. Together, these components formed a very balanced objective that guided the agent towards clinically realistic and safe solutions, which made it capable of achieving strong tumor control while minimizing toxicity and also maintaining treatment practicality. Now, moving on to the code. This code defines the stepwise reward the agent receives after selecting each beam. The high-level objective is to maximize tumor coverage while minimizing dose to surrounding healthy organs, and do so in a way that's clinically meaningful. We start by normalizing doses to avoid numerical instability and extract the tumor region, since all coverage calculations are relative to PTV voxels. If for some reason there is no PTV mask detected, which would signal corrupted data, we immediately return a negative reward to discourage invalid states. Next, we compute the change in tumor dose coverage. This is the primary positive signal. When a beam increases the number of PTV voxels receiving therapeutic dose, the agent receives a reward proportional to that improvement. This helps the agent be guided towards the angles that progressively improve tumor coverage rather than relying only on terminal feedback. We also introduce penalties based on OAR dose changes. For each OAR structure, if its dose increases due to the beam, we subtract a weighted penalty. Organs like the brainstem and spinal cord are penalized more heavily than carotids, reflecting clinical toxicity priorities, since the brainstem and spinal cord are more sensitive regions. In the terminal step after the final beam, we apply additional bonuses or penalties based on final treatment metrics. The final PTV coverage exceeds clinical threshold, say 95%. The agent receives a strong terminal bonus. If coverage is poor, it receives a penalty instead. Similarly, a high D95 receives bonus or a reward, encouraging not just coverage but coverage uniformity. We further evaluate the OAR dose at the end and penalize solutions where an OAR exceeds tolerance, mimicking real-world dosimetric constraints. Finally, we clamp the reward range to stabilize learning and avoid exploding values, which is a common trick in reinforcement learning pipelines. Essentially, the design of the reward embeds clinical trade-offs directly into the RL agent's objective, prioritizing tumor coverage first, then promoting dose uniformity and penalizing OAR exposure, all while keeping the beam selections efficient. You can think about it in you can think about this reward function like training a pilot in a flight simulator. Each time the pilot adjusts the controls, the system gives feedback. Did the plane stay on course, avoid danger, and maintain altitude? That's exactly what we do here. Each beam angle is like nudging the controls. We reward the agent when it flies towards the tumor, improving coverage, and we penalize it when it flies too close to the danger, meaning excess dose to healthy organs. At the end of the flight, or in our case, after selecting all 5 beams, we look at the final outcome. Was the mission successful overall? If yes, we give a big terminal reward, and if not, we apply penalties. So the agent isn't just guessing beam angles, it's learning how to make safe, effective navigation decisions step by step towards a clinically optimal treatment plan. Now that we have covered the design of our reinforcement learning system and the logic behind the reward function, let's move on to the results and the clinical evaluation phase. This stage is where we validate whether the agent's decisions translate into meaningful improvements in real treatment planning terms. Our evaluation focuses on 3 key aspects: dosimetric accuracy, dose volume histogram metrics, and overall clinical performance compared to existing beam angle optimization methods. We test the train model on held out patient cases from the OpenKBP dataset, which we introduced earlier. These cases are not used to train the model at all. The model hasn't seen these cases. It is being evaluated on cases which it has never seen before. So the goal is to measure how well the agent will generalize across diverse anatomical variations and planning challenges. By analyzing outcomes like PTV coverage, D95 scores, and OAR sparing, we can quantitatively assess if reinforcement learning truly achieves plans that are both efficient and clinically sound. Essentially, this section ties the entire workflow together, bridging the algorithmic optimization process with its clinical relevance and real-world viability. So now let's walk through the evaluation setup we used to test the model performance. We evaluated our approach on a held out set of 100 head and neck cancer patients, which followed the open KBP standard. This ensures that we are testing across a wide anatomical range and tumor presentations, which is important for demonstrating generalization. For each patient, we worked with a 2D mid-slice representation. While full 3D data is ideal, this mid-slice approach captures the most clinically relevant anatomy while keeping computation efficient, helping us rapidly iterate and validate beam angle learning. To measure the treatment quality, we rely on the standard metrics we have used so far. This includes the D95, the mean doses to OARs, and the overall coverage percentage. Finally, during evaluation, the agent used a greedy strategy, meaning epsilon is set to 0. So instead of continuing to explore, it selects the best beam angles based on what it has learned, similar to how a trained clinician would rely on expertise rather than trial and error. Together, this setup ensures that a performance comparison is clinically meaningful, computationally realistic, and aligned with how models would eventually operate in practice. Let's now move on into the dosimetric performance outcomes, which evaluate how well the RL agent actually performs in terms of real clinical radiation planning goals. We'll begin with the target coverage. Across the testing data, the agent achieved a mean D95 value of about 0.2365, normalized to prescription dose. While this is moderate, what is promising is the mean coverage of over 80%, and in some cases, the agent achieved 100% PTV coverage. This indicates that the system learned to consistently prioritize delivering the therapeutic radiation to the tumor, which is the core clinical objective. Now let's discuss the OAR pairing. The results show strong protection of critical anatomy, while you can only see, oh no, the spinal cord received essentially zero dose, which is excellent given its high sensitivity. The brainstem dose remained extremely low, around 0.02, well below tolerance thresholds. The parotid glands, which impact long-term quality of life due to salivary gland function, stayed within an acceptable range around 0.25 to 0.232, meaning the system managed xerostomia risk reasonably well. The mandible dose averaged around 0.22, showing controlled exposure and low risk. Overall, these results demonstrate that the RL models trained successfully learned to balance tumor coverage with meaningful organ at risk protection. It didn't just push dose everywhere, it developed clinically sensible trade offs, which is a key benchmark for medical AI. Here we see how the RL agent has developed its own beam configuration strategy. And what's remarkable is that it mirrors real clinical intuition. The agent typically settles on a 5 beam setup, for example, at angles like 180 degrees, 350 degrees, 10 degrees, 0 degree, and 340 degree, as shown. These beams aren't placed symmetrically at random. They are strategically distributed around the patient to achieve both broad target coverage and precise dose delivery. If we look at the geometric pattern, we notice that the beams tend to cluster along the tumor's major axis. This means that the model is learning to align the beams with the tumor's natural shape and orientation, ensuring that the radiation dose is concentrated where it's needed most. Or at the same time, the agent also intelligently avoids the trajectories that would pass through sensitive organs. This is especially visible in how it learns to protect the spinal cord and brainstem. The posterior beams are minimized automatically without any explicit instruction. So what's happening here is a clear example of emergent learning. Through feedback from the reward function, the system internalizes the same reasoning a human planner would use, balancing tumor coverage with organ safety, and reproduces that logic autonomously. Now on this slide we are looking at a core clinical evaluation tool, the dose volume histogram, or the DVH. The DVH is essentially a summary of the 3D radiation dose distribution within a structure, condensed into a 2D curve. It plots the percentage of a structure's volume that receives at least a certain dose level. This makes it extremely useful for comparing how well a plan covers the tumor while sparing normal tissue. The key metric derived from the DVH is the D95. Clinically, a high D95 indicates that nearly the entire tumor is receiving the prescribed therapeutic dose, which is essential for effective treatment. On the right, you can see an actual DVH obtained from one of the patients in our test set. The blue curve represents the target volume, while the orange, green, and red lines represent different organs at risk, like the parotid glands and the mandible. Notice how the target curve extends towards higher dose values while the organs at OAR curves drop off much earlier. That's exactly what we want to see. Strong target coverage with effective sparing of surrounding healthy structures. So this DVH visualization is both a validation of the agent's decision making and a clinically interpretable proof that the learned beam angles are achieving high quality treatment plans. So now what you're seeing is a spatial visualization of the dose distribution for one of the test patients. What you're seeing here is a mid-slice dose heat map overlaid on the patient's anatomy. The cyan contour line outlines the planning target volume, the PTV, or the tumor region. The bright color bands represent the paths chosen by the RL agent. Notice how the dose is concentrated precisely around the tumor boundary, forming a high dose region, while avoiding unnecessary dose spill into the OARs. This reflects a clinically desirable behavior, and we want to deliver enough dose to guarantee tumor control, but at the same time minimize radiation exposure to critical organs nearby. This type of visualization is important because numerical metrics like D95 and OAR doses only tell part of the story. Spatial maps let us visually confirm treatment quality and ensure the dose is delivered in a physically meaningful, clinically safe way. To illustrate how the system operates on real data, real clinical data, I am showing an example patient from the test set. Uh, On the left, you have the input to the model, a CT slice with the tumor contour highlighted in cyan. This is the only anatomical reference the agent sees. There's no handcrafted planning guidance, no human beam templates, just the raw anatomy and the tumor boundary. On the right, we see the output generated by the RL agent, the optimized beam configuration and the resulting dose distribution. You can see how the beam converges precisely towards a target without uh, compromising, or sorry, while avoiding critical structures in the surrounding head and neck region. This patient was never seen during training, so this result demonstrates true generalization. The model learns anatomical patterns and dosimetric trade-offs and then applies them to new unseen cases. Visually, we can appreciate two things. First, the tight tumor coverage, and second, very controlled dose outside the target region, which is exactly what we aim for clinically. So now you can see the DVH of the patient whose CT slices and the optimized beam angles we have already seen in the previous slide. So this curve will help us validate how the RL selected beam configuration performs in terms of the dose metrics. So as I've described earlier, the blue curve corresponds to the planning or the PTV, and you can see that the curve drops sharply near normalized dose equal to 1, meaning almost the entire target receives close to the full prescription dose. This steep right shifted fall off is a hallmark of a strong tumor coverage and good dose homogeneity. The remaining curves represent key organs at risk, in orange for the left parotid, green for the right parotid, and red for the mandible. These curves sit far to the left, which indicate that only a small fraction of these structures received even moderate dose levels. Most of the volume of these sensitive structures did not receive any dose levels or very low dose levels. This pattern demonstrates favorable trade-off, high tumor dose, sharp gradient, controlled exposure to salivary glands and bone. Importantly, it is not a hand-picked case, as I have been saying repeatedly. This reflects a performance often on an unseen patient, suggesting good generalization of the RL agent. To further argue our case of generalization, here is another example from the test set. So you can see the CT slice with the tumor region outlined in cyan. This is the anatomical input provided to the RL agent, and on the right you can see the predicted dose distribution along with the beam configuration, of course. So once again, you can see that the beams are intelligently directed to concentrate around the tumor while minimizing exposure to the OARs. This also further demonstrates the model's ability to adapt to new patient geometries and optimize angles without any manual planning intervention. So this is another DVH curve. This time, this is the DVH curve for the one we saw in the previous slide, the patient we saw in the previous slide. So the blue curve represents the PTV, and you can see it sharply rises near a normalized dose of 1, indicating tumor coverage and also no low OAR dose. You can also see that the orange and green curves, these represent the salivary glands, as I've already told. Most of their volume sits around very low dose values. In particular, you can also notice the tall green peak right near zero. That spike means that the majority of the right parotid gland receive almost no radiation at all. Clinically, this is a very desirable metric because it reflects excellent organ sparing and directly translates to better preservation of saliva production and patient quality of life. So this is another real life test set case. So you can see that the cyan boundary marks the PTV, and on the right you can also see the dose distribution generated by the RL agent and the optimized beam angle distribution. So as you can see, the model generalizes well on unseen patients. This is the DVH curve for the patient on the previous slide, and I don't think I have much to say over here. You can see that the blue curve is strong, has a strong peak at near 1, which indicates good tumor coverage and low and great OAR sparing, while you can see all other curves are more towards 0 and have low to moderate doses. So now this is a more detailed breakdown of our results across the whole testing dataset, which consisted of 100 patients, 100 unseen patients. On average, the model achieved a D95 of 0.2365 and coverage of 80.4%, closely matching the earlier reported summary. This indicates that the agent consistently delivered therapeutic doses to most of the PTV. When we look at the critical organs, the spinal cord received effectively zero dose, while the brainstem averaged just 0.02, both comfortably within clinical tolerance. Overall, these values reinforce that the RL agent didn't just perform well on a few patients, it generalized. Across nearly 50 independent test cases, it learned a consistent balance, maintaining strong tumor coverage while minimizing dose to critical structures. Now, what you can see are the learning dynamics of our DQN training run. These are the training curves. So on the left, you can see that the loss drops sharply at the start as the model learns, but after that it oscillates and even rises later in training. This behavior is normal in reinforcement learning, unlike supervised learning. Increasing loss does not necessarily mean the model is getting worse. Instead, as the agent explores higher reward strategies, Q value estimates shift, leading to temporary loss increases while the actual policy strengthens. On the right, you can see that the reward curve steadily increases, which is the true signal of learning here. This clearly shows that the agent is improving its beam selection policy over time and learning to cover the tumor while minimizing the dose to OARs. Together, these curves confirm stable and convergent learning dynamics. Now let's move on to the validation data performance. So you can see the validation D95 versus epochs on the left, and on the right you can see the validation coverage versus epochs. So I trained the model for a total of 50 epochs, and these curves demonstrate how well the policy generalizes to unseen patients. Starting with D95, this metric reflects the minimum dose delivered to 95% of the PTV, and over training we can see gradual upward trend rising from about 0.1 to 0.16 despite some noise. These are in normalized units. So this is expected because RL signals are inherently stochastic, inherently meaning they are random, especially early in training. What matters is the overall upward trajectory, which indicates that the agent progressively learns to improve tumor dose coverage in a clinically meaningful way. On the right, you can see that the validation coverage also follows a similar trend, improving from around 0.72 to 0.79, which corresponds to 72% to 79%. This shows that the learned policy generalizes beyond the training data and maintains strong tumor coverage across varied patient geometries. One observation worth noting, the training loss earlier in the learning curve increased even though rewards and coverage improved. This is expected in RL systems. Unlike supervised learning where loss must strictly decrease, the DQN loss the DQN loss reflects the Q value estimation error, not the clinical quality. As the agent explores more effective beam strategies and receives larger reward signals, the magnitude of the Q value updates increases, often causing rising loss values. In RL, rising loss does not mean worse performance. It often correlates with learning more aggressive and higher value strategies. Now, to summarize, these validation curves verify that the improvements observed during training are not simply overfitting. The RL agents learns the RL agent learns progressively better treatment configurations that are generalizing to new patients. Now we are going to talk about the limitations and the constraints with this model. So from what we have discussed till now, we know that RL can learn clinically meaningful beam placement behavior, but there are still few intentional simplifications worth noting that make the problem computationally tractable in a research setting. First is the dose calculation approximation. We operate on a 2D mid-slice approximation instead of a full 3D dose engine. This accelerates our training but simplifies tissue heterogeneity and scatter physics. And a full 3D dose model would be the next natural extension. Second is the fluence simplifications. The beams are modeled using Gaussian line dose profiles without fluence modulation or monitor unit optimization. In clinical planning, fluence shaping is crucial, and this will increase the D95 metric to clinical levels, like above 90%. Third, as I mentioned, the clinical gap in D95. Our D95 is around 24%, which is well below the clinical benchmark. And the system learns where to aim, but the underlying dose model limits absolute performance. But since our model's inherent aim was beam angle optimization, as it says in the title, so we have learned on tumor coverage, and the system learns where to aim for the tumor. So the computational bottleneck for me was that the training was done CPU only, which restricted the scale and the hyperparametric tuning. The GPU accelerated dose simulation will allow more complex architectures and faster conversions. The key point in while The point to be noted in these limitations are that these are engineering constraints, not the failure of algorithms. They outline a clear roadmap for full 3D dose modeling, fluence optimization, and GPU accelerated learning to move toward clinical capability. So to wrap up here are the main directions we can plan to make this to extend this project. So we can move to a 3D dose calculation as mentioned in the earlier slide. We are right now using a 2D slice for faster training, and we can use proper 3D dose calculations. So through that we can also model tissue differences and the scatter more accurately, just like clinical systems do. We can try better RL algorithms. We have right now worked with DQN. There are many other advanced RL algorithms that may provide smoother learning and better performance. We can use a smarter reward function. Right now, we were using linear reward functions. We can start to use non-linear reward functions to model in our model so that it learns these relationships quickly and more accurately. And lastly, we can integrate these with real treatment planning systems. So this will help in optimizing beams and the intensity, the beam angles and the intensity together. Basically, the model works, and now we focus on making it more realistic, more accurate, and closer to real world clinical use. On a final note, this work presents one of the very few reinforcement learning based pipelines for the automated beam angle optimization of radiotherapy. The agent successfully learned clinically consistent beam placement strategies directly from data without relying on any manual rules or fixed templates. The first key takeaway is that this is a novel RL-based beam angle optimization pipeline. It is one of the few comprehensive implementations of DQNs for radiotherapy beam configuration. Secondly, the key takeaway is that the system demonstrates end-to-end automation. There were absolutely no manual interventions in the entire beam configuration process. Finally, this also establishes a promising clinical direction. Despite working with simplified dose models and using 2D slices only instead of 3D, the results show quantifiable improvements in tumor coverage and OAR sparing, indicating strong potential for AI-driven treatment planning. Overall, the results prove feasibility, establish a scalable framework, and open the door for more physics-accurate, clinically deployable RL-based planning systems in the future. Thank you.